All right. So what we're looking at today are the spectrums of various stars. So in your notebook, we're going to draw something, and we're going to go over and I'm going to demonstrate something for you using some light passing through some different gases. And we're going to use this information to actually figure out how is it that we know what we know about stars. Stars are so far away. We've never actually been to one. Granted, we've got our sun, which is a lot closer, but the next closest star is 4 light years away, which may not mean a whole lot to you right now, but basically the fastest ship we've got, the fastest rocket we've ever made. It would take a little over 40,000 years to get to the next closest star to us. So we've never actually been to these things. So how do we know how big they are? How do we know what color they are? How do we know how far away they are if we can't get there? Well, it's all about the electromagnetic spectrum. But title the page, Spectrums of Stars. So just a real brief review. You probably dealt with spectrums before, but say when we have like a prism and light travels through that prism. When it hits the prism, the light gets refracted and bent. And as it's bent and comes out the other side of the prism, you end up getting the different colors. And they're in the Roy G. Biv order. So you've got the red, orange, yellow, green, blue, maybe one more, and we'll just add violet there. I know I forgot the indigo, but so you've got the colors with the rainbow coming out. Well, this is a part of the electromagnetic spectrum. It's the part that we can see with our eyes, the visible light. Well, when we actually take the light from a star and we pass it through something like a prism, the light from that star will break out into the spectrum, and we can see all of the different colors coming off of that star. And those colors and things that exist inside of that spectrum tell us a lot about the star, including what it's made of. And if we know what it's made of, we can tell a little bit about how hot it should burn and how bright it should be, and that gives us a lot of what we need to tell how far away those things are. So on your notebook page, I want you to draw 3 rectangles. These rectangles are just for you to actually sketch the spectrums coming off of the 3 or 4 different gases that I'm showing you. Let's do 4, because I think that actually I'm going to show you 4. Okay, and so we'll just number them. This is spectrum 1, spectrum 2, spectrum 3, and spectrum 4. And off on this side, you're actually going to name the gas that we're passing it through, so you'll write the name down. And then you're going to sketch in here what the spectrum looks like. Now, to give you an idea of kind of what you're looking for, the spectrum is going to come through and you'll see the colors, but you're going to see what we call gaps in the spectrum. Gaps in the spectrum are like where the color doesn't exist and it should. Because you know off of a rainbow, all of the colors exist and it's seamless. It goes straight from red into orange into yellow into green, all of that. But here, you'll see a black area where there's no color at all, and there should be. And you're going to draw those gaps for me, and you'll see what that looks like here in just a second. Okay, I'm going to swing around here. We're going to turn out the lights. Okay, and we can actually kind of test this a little bit. So we've got the diffraction rating on the iPad. So we'll see light coming off of the window. There's not a whole lot of light coming through because the blinds are closed. You can actually see the spectrum. You can see the colors coming through a little bit. I'm going to turn the lights back on. Look at the ceiling. When you look at the ceiling, you can see a little bit of the spectrum coming off of that. Okay, I'm going to turn the light on my iPhone on. The light on my iPhone. Different kind of spectrum coming through. So each kind of light gives off a slightly different spectrum. But you can also have different elements give off different spectrums. And so when we actually ignite an element, by either passing electricity through it or something like that, the light that comes off of the element itself tells us a lot about that element. And actually it's called the element's thumbprint. And so I'm going to turn this on. This one is helium. So in that gap right next to your first rectangle, go ahead and label that helium or He. And then you'll see the gaps now, and it's flickering a little bit. You see lots of different spectrums coming off of it. look at one of them and sketch the gas that you see. Now, I can't leave this on forever, so if you need to, pause the video and sketch your gas. And then we'll move on to the next one here in just a couple of seconds. Okay, so that one was helium. Let's take this bulb out. This next one, put it up. This next one is hydrogen. So we've had helium, now we have hydrogen. Now look at just one of the spectrums coming off of it. It should look quite a bit different than the helium one did. The gaps are in different places, and if I remember right, the gaps are actually quite a bit larger and in different locations. So sketch the gaps on this one. And you don't have to make an absolute perfect sketch. You don't have to be an exact replicate of it, but just get them in there so you can tell it is definitely different. And I'll give you a couple of seconds. This next one is nitrogen. So third one down, going right in there, nitrogen. Again, spectrum coming off of nitrogen looks different than hydrogen and helium. The gaps are in different places. Sketch that one. And this last one is actually not a pure element. This one is actually a compound. This is carbon dioxide. Now, something about stars and the way that they work, stars won't ever actually have a compound in their composition. They won't have CO2, for example. And the reason for that is because they're taking hydrogen and they're fusing them into the other elements. So you're only ever going to get pure elements in a star. But I'm showing this one to you, even though it won't appear in a star, so that you can know that CO2 has its own thumbprint, has its own spectral gaps, and because it's got its own spectral gaps, just like the other elements do, we can say with certainty that CO2 is not found in other stars. So this is an example to show you how we know what isn't in stars, because we know what these things do look like when they're present.